Hey there, how's it going? So to start off, to find the derivative of sine x, we will have a look at what the graph of sine x looks like and consider the gradient function on it, as we've been doing with some other functions and figuring out their rules for differentiation. Alright, so let's say we've got this graph here. Of sine x. That's a little bit too semicircular, but hopefully you get the point. We've got pi on 2 and 3 pi on 2 then. Okay, so let's consider some points along the function, some tangent lines, and then the gradient of those tangent lines. So normally the pretty important ones we want to look for are where the gradient would be 0, so say here, right, where there's a horizontal tangent, gradient 0 there, and also over here as well. So on the gradient function of sine x, we're going to have a pi on 2, we're going to have a value of 0, and a 3 pi on 2, we're going to have a value of 0 as well. So then this breaks up at least this chunk of the x-axis into a few different regions, so let's consider what's happening in between each of them. Alright, so in between 0 and pi on 2, we're going to have we've got positive gradients, and likewise after 3 pi on 2 up until 2 pi, we've got positive gradients as well. And then in between pi on 2 and 3 pi on 2, then the gradient of the tangent lines here are negative values. So we want a function which has positive values. At pi on 2, it's got a value of 0. In between pi on 2 and 3 pi on 2, it's got negative values. At 3 pi on 2, it's got a value of 0, and then between 3 pi on 2 and pi on 2, it's got positive values. So what function comes to mind? Hopefully another trig function, either sine x just shifted back, or cos. Now I guess the question is it going to be exactly cos x, or is it going to be like cos x stretched or compressed? Because unless we were doing this maybe properly to scale and actually measuring these tangent lines, is say the tangent line at 0 here, is the gradient of the tangent here 1, or is it like maybe 2 or a half, or sometimes exact trig values 1 on root 2, something like that. Okay, but maybe we know that we're going to have something kind of like this. So maybe the gradient function of sine x is cos x, or at least some constant multiple of cos x. And of course, how are we going to figure out what it is precisely? We'll go and use the definition. Okay, so if we've got sine x, the gradient is going to be the limit as h goes to 0 of the difference quotient, where we take the difference of inputting x plus our step size h minus inputting x, so our original function, all over that step size of h. Okay, so that's just using the definition of the derivative. Okay, not too much we can do with the sine x or the h there, but sine x plus h, we know our angle, if we know at least, our trig angle sums, then we can change this expression to, we're going to have sine x cos h plus cos x sine h. Right, so sine and cos and sine and same sign, S-I-G-N in the middle. for sine, that's the reverse for cos. And then we've still got our minus sine x all over h. Okay, so what can we do here? Well, notice at least we've got two terms with the sine x in it, so we can at least take them out as a common factor. So we've got sine x and sine x outside of cos h minus, that's one lot of it. And then we've got plus our cos x sine h all over h. All right, so now we've got a fraction with multiple terms in the numerator, so we can split up this addition into sine x cos h minus 1 over h plus cos x sine h separately over h. Then because we're taking the limit of a sum is the same as the sum of the limits, so I'm going to do like two moves here in one go. So we're going to have the limit as h goes to 0 of sine x cos h minus 1 all over h plus the limit as h goes to 0 of cos x sine h over h. Alright, now with both of these, they have in their numerators a trig function of x, but since we're taking the limit with respect to h, we can treat these like a constant and bring them outside the limit, just like we did back in the constant multiple video and when we were deriving the rule for the product rule. Okay, so we've got sine x times this limit, cos h minus 1 all over h, plus we've got cos x times this limit here, sine h over h. Okay, so our hypothesis was maybe we could end up with sine x differentiates to cos x, and we can see when we apply the definition of the derivative, we end up with cos x here and sine x times something. So for this to be true, we're hoping that this limit here ends up being 1, because then we'd have cos x times 1, gives us cos x, but we don't have any sine x term here. So we're probably going to also hope that this is sine x times whatever this limit is 0. So we end up with sine x times 0, which is 0, plus cos x times 1, which is just cos x. One way you could evaluate these limits is do a kind of hacky method, and in your calculator in radians mode, of course, not fake degrees. Input h is like some really small value, like 0.00001, so cos of that, minus 1 over 0.00001, as long as you have the exact same actual decimal you're putting in, and you can, from that fraction, hopefully see, as you get a fairly small number close to 0, you can see what it is. And if you do that, you will in fact figure out that this is 0 and this is 1. We could do that, but you're looking at the video and you're seeing, knowing how much I waffle, it's probably going to say 30 minutes or something. So we're not going to be done yet. Now, this would be the cheap and nasty way. What I want you to imagine, you've had long day at work, you just want something for RVT, you're driving home. You could do a cheeky Macca's run and just plug them into your calculator, and it'll fill up your tummy. But it's probably not going to be deeply satisfying. What you really want to do is you want to engage in some delayed gratification. You want to drive home. Kids come running out the door to greet you. You walk in, your wife's there, nice sundress, barefoot in the kitchen, baking, wisp of hair glints in the sunlight, and you get freshly baked muffins. they're going to fill you up, and you're going to feel full. That's what we're going to do. I have been known to do the have a cheeky nug run, metaphorically, in class, given the nature of the class. Teachers, got time constraints, time pressure we feel. But what we truly want, let's go for that drive home and get our trad wife's baked goods. So what we're going to need to do to figure out this limit is we're going to draw up our unit circle in the first quadrant. And this is going to take a little bit of work. So recall from the unit circle definition of our trig functions that we have cos x is this distance here on our x coordinate, right? So our x coordinate of this point here is cos x, and then sine x is the y coordinate. And then so that matches with what you normally learn first in right angled trig, that sine of the angle is opposite over hypotenuse, and cos is adjacent over hypotenuse. Sine over 1, right, because this is the radius of a unit circle. Sine over 1 is sine. Oh, I should have written, excuse me. My brain wrote x's because we did them over here, but since we're talking about this angle here, we should have the x coordinate of this point is cos of that angle, and the y coordinate of that point, so that height there is sine of that angle. Okay, so I'm going to give some points some labels so we can refer to them a bit better. So we've got, of course, our origin here. Let's go like, we've got A point there and point B there, and we'll have point C here. Okay, so what I want you to do is, first of all, look at this height AB, which is of course just sine theta by the definition of the unit circle, and then look at this arc length AC here. So I'm going to write an expression here, which is hopefully fairly acceptable. That length there, AB, is less than or equal to the length of arc AC. And we show this technique using a fairly sophisticated method called proof by eyeballs. Well, you've got to get from this distance to here, right, is going to be equivalent from this distance to some, on like some parallel line up there, right? So that distance there is going to be the same as that distance there. But then if you were to curl out this AC, it's clearly going to be above there, right? Because the shortest distance between any 2 points, at least on a Euclidean geometry, is going to be a straight line. So when you curl that out, it's going to be bigger. We'll say less than or equal to, because equal to maybe when when theta is in fact 0, so then sine theta, the y coordinate, is 0. Okay, so AB is sine theta, and arc AC, well, in radians we have the arc length formula that L equals r theta, so L equals 1 radius times theta, L equals r theta for arc length AC. And then for our purposes, we kind of want an expression that looks like sine of our variable, like here it's h, here I'm using theta, doesn't matter, right? We could have had x, 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 or y, 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 or, alpha, alpha, alpha. So the relationship between the variables, which is important, not really the particular name we give them. So I'm just going to divide theta over by this side. Do we have to worry about flipping the inequality? Well, we're just talking about like a positive. Remember, we're going to be talking about theta or h down here going towards 0, and you can imagine we're just kind of like talking like in this first quadrant here, right, where we're talking about like an acute angle. So by definition, we're really just talking here about an angle between 0 and pi on 2, as you can see at least in the diagram. All right, so this gives us that sine theta on theta is less than or equal to 1. Okay, we're hoping, remember, that it is in fact just simply equal to 1. All right, so another thing we can do is, I'm going to add in a different color, is look at this line here. Okay, and I'll give this a new point there, D. So if you weren't aware, this distance here is tan theta, right? This is right angled because if we have a tangent line, which is where the name tan actually comes from, if we have a tangent line at our circle, it's going to be at right angles to the radius. Okay, and you might just know, I know for example, when I just introduce unit circle definition, I go sine theta, cos theta, and then tan to connect it to right angle trigonometry is opposite over adjacent, which ends up being the same as sine over cos y coordinate over x coordinate. But here, if you look at triangle, where's theta? Theta's here. So we've got, actually maybe if I point with the starting where the right angle is, if we've got angle triangle A, B, O is going to be similar to triangle, flip my head around here, triangle D, A, O. And so since they're similar triangles, their sides are going to be in the same ratio. So we've got, what have we got again? So we've got the sides next to the right angle and the sides next to the right angle here. We've got AD over AO is going to be the corresponding sides in the similar triangles with AB and OB, which means tan theta over 1 in triangle like DAO is going to be the same as sine theta over cos theta in triangle ABO. So that's where, because of similar triangles, and sine theta over cos theta definitionally is tan theta, this tangent line here gets extended out there, and then that is also tan theta, that length there, AD. Okay, so we're going to get a different expression, another inequality, using where we've got tan theta there. And this time, instead of using the arc length formula, we're going to use the sector area formula, but in radians. Okay, so we have that this sector here, right, from AO through to C, right, so this sector from our unit circle, that area there is clearly covered by triangle ADO, right, is fully contained inside triangle ADO, plus it has that bit there. So clearly this sector area, so we've got sector area of sector, what is it, AOC, is less than or equal to the area of triangle AO and D. All right, so what is an expression for the area of sector AOC? Well, it's half r squared theta in radians. So we're going to have half times the radius is 1 squared theta. And that's going to be less than or equal to, triangle AOD is right angle triangle, so we can just do a more basic formula, half times base times height. So half times AO, which is 1, times height tan theta. Alright, so here we've got half times 1 squared is half, and half times 1. So if we divide both sides of the inequality by 2, both of this stuff disappears, and then we've got theta is less than or equal to tan theta, and tan theta we can write as sine theta on cos theta. So now if I just do the old switcheroo with these guys here, right? If I multiply cos theta up to that side and then divide theta down to that side, we're only talking about positive values here, we can have that cos theta is less than or equal to sine theta on theta. I'll just section these off. Alright, so now we've got two inequalities that cos theta is less than or equal to sine theta on theta, and also sine theta on theta is less than or equal to 1. So we've got this exact same expression here that's less than something and that's greater than something. So we can write basically this bit over here and write them all in one go. So we've got cos theta is less than or equal to sine theta on theta, which is less than or equal to 1. Note the conspicuous gap here. Okay, so we can take, just like we could, like if we add 1 here, we've got to add 1 here, or if we times this by 2, we've got to times throughout by 2. We can, because we know that this expression is true, we know if we do anything to all three of these, it should also be true as well. So what we're going to do is take the limit, since we've got the variable theta here, the limit as theta goes to 0, the limit as theta goes to 0, and the limit that theta goes to 0. So what's the limit as theta goes to 0 of cos theta? Well, we can just simply compute it by subbing in 0. So cos of 0 is 1. Now, we're not really sure what this is. This is like what we're trying to find. You can see here, exact same relationship, but just theta instead of h. And what's the limit as theta goes to 0 of 1 of a constant? Well, everywhere you see theta, sub in 0, and we're not dividing by 0, it's pretty safe to sub in 0, and so what are we left with? 1. Okay, so we know that the limit of as theta goes to 0 of the expression sine theta on theta is both bigger than or equal to 1 and less than or equal to 1. So there's a fancy word for this called the squeeze theorem, but like obviously if it's sandwiched between two values and also equal to these two values, if it's less than or equal to 1 and bigger than or equal to 1, well, the only thing that can satisfy both sides of that inequality are that it is in fact just simply equal to 1. So this limit here is equal to 1. Right, so that means over here we know that the limit as some variable goes to 0 of sine of that variable over that variable is 1. Alright, so we've got to still deal with this bit here, cos h minus 1 over h, and its limit as well, right? Because maybe I was wrong, maybe it's not just cos x, maybe we've got sine x times something, and we've got a sine x plus a cos x, and it's some other curve once you smush them into one of those trig functions. Okay, so we have to deal with which bit here? This expression here. So we've got the limit as h goes to 0 of cos h minus 1 all over h. Alright, so in the fraction inside the limit, I'm going to times top and bottom here by kind of like the conjugate there of that expression. Okay, and then the benefit of that is going to be that we have a difference of 2 squares in the numerator, so cos of h and 1 with a minus in the middle and plus in the middle is going to be cos of h all squared, which we write as cos squared h, and minus 1 squared, which is 1, all over this times this, which I'm going to leave factorized because later we're gonna pull it back out. All right, we know that cos squared plus sine squared is 1. So that means if we take that sine squared and subtract it over to the other side, using the standard Pythagorean identity, that cos squared is 1 minus sine squared. So I'm going to replace that in there. Alright, so here we're going to have our positive 1 and minus 1 cancel, which is nice because now we've just got one term, right? We started with 2 terms in the numerator, right? So like we could say like this is cos h over h minus 1 over h, but like what are we ever going to do with that 1 over h, right? We can't sub 0 in, and if it's just 1 there's not much we can do with it. But this is kind of nice because we've got one term left in the numerator, and then we've got a factorized denominator. Okay, I'm going to write this sine h as sine squared rather, as I'm going to say this is the same as sine h times negative sine h, all on h times cos h plus 1. And then recall, if we've got the limit of a product will be the same as the product of the limit. So I'm going to keep this like this over this times this over this and separate them out into separate limits. That's nice. Didn't we just show what that was? Well, we just showed that that bit there was 1. And that's going to be times the limit as h goes to 0 of negative sine of h all over cos h plus 1. Alright, so what are we going to do with this? Well, I mean, we'd normally be a little bit tentative, given all the rules that we've figured out. But we can actually, there's no problem with subbing in 0 at this point, right? Because we're going to get negative sine of 0, and sine of 0 is 0 over cos of 0 is 1, and then we've got our plus 1 there. Negative 0 is 0 over 2 is just 0, and 0 times 1 is 0. And so we get back over here, we now know that this bit here, limit as h goes to 0 of cos h minus 1 all over h. This limit here, we found out, is in fact 0, and so sine x times 0 is 0 plus cos x times 1 is cos x. Right, so to conclude, we've got that when we have the function y equals sine x, the derivative is cos x, which matches up with what we thought from this analysis over here of the graph. Alright, so of course there are a few other trigonometric functions which we may want to know their derivatives as well, but since I like to kind of, if you haven't noticed, keep each concept to to one whiteboard. I'll continue this in a separate video. So that's it for this one. Catch you later.